All right, good afternoon. Welcome back to Calc 2. So we started improper integrals yesterday. We are going to continue doing some improper integrals today. So let's go ahead and get started with that. So what do we have here? This is probably the most famous one, okay, or at least one of the most famous ones. And that is when we have the integral of 1 to infinity of 1 over x dx. All right. So, first thing we're going to do is we're going to go ahead and turn this infinity into a limit. So we have the limit, pick your favorite letter. T goes to infinity of 1 to t, okay, of 1 over x dx. All right. So what are we going to have next here? We are going to have, we can just integrate this directly. This is the one that you know. Okay, so this is going to be natural log of x evaluated from 1 to t. I need a limit because we don't know what t is. Okay, so this is equal to the limit. T goes to infinity of natural log of t from 1 to t. Now, these are all positive numbers, so we don't really need the absolute values anymore, so I'm going to go ahead and nix them. So we're going to have limit as t goes to infinity of natural log of t minus the natural log of 1. Natural log of 1, we know that is 0. And if we look at the graph for natural log of t, right, and then we can see that natural log of t goes up, up, and away, slowly, but it does go off to infinity. So this limit is infinity, and hence my integral diverges, doesn't go to a number. Okay, so that is, that's a very famous case. Okay, we're going to revisit this one toward the end here. Okay, so I've got a couple of other cases that are pretty famous or pretty well known, so I'm going to watch out for. How about we try this one? This is integral from negative infinity to positive infinity, okay, of dx over 1 plus x squared. Okay, now you need a stopping point in the middle. I'm going to pick the obvious one because 0 seems to be like an obvious stopping point. So we're going to have the limit, say, of a goes to infinity, integral from 0 to a dx, 1 plus x squared dx, plus, and then we're going to have another limit here because all I did was take a convenient point, and this is going to be b goes to negative infinity of b up to 0. Is there anything magical about 0? Not really. You could have chosen 1 to a and then b to 1. Okay, it really wouldn't have mattered. There'd be more stuff to deal with in the middle because 0 is a very convenient point, but there's nothing magic about having to have picked 0. I mean, you could have picked, we could have gone from 101 to a and then b to 101. Okay, infinity, negative infinity to positive infinity was, I said, in the middle, but there isn't really any middle. Any point you happen to take is the middle between negative infinity and positive infinity. Okay, so pick a convenient point, and since I know what this integral is going to be, 0 happens to be convenient. 0 is convenient for a lot of integrals. Okay, so I recommend the 0, but you do what you want. Okay, so here we're going to have, and we are going to say this is going to be the limit as a goes to infinity. That's a nice arrow, isn't it? Okay, a goes to infinity, and this is going to be the inverse tangent of x from 0 to a, plus limit as b goes to negative infinity, and then we're going to have b to 0 with the inverse tangent of x. Okay. We're going to go back and we're going to say, okay, well, this is going to be limit as a goes to infinity of the tangent inverse of a minus, we don't need a limit because this is tangent inverse of an actual number, 0. Okay, so that's this area. And we have plus, and I have the tangent, well, yeah, tangent inverse of 0 minus limit of b goes to infinity, negative infinity, tangent inverse of b. All right, so here's my integral A, my first integral, the region for the second integral. Okay. Same integrand, but different region. Well, as a goes off to infinity, right? What is tangent inverse of a going to, right? What is the graph of tangent of a, inverse tangent rather, something like that, right? And there's an asymptote here. You guys remember this from somewhere? Okay, so that integral, right, that limit rather, is pi over 2. So we're going to go ahead and say, well, that's going to be pi over 2, right? That's evaluating this first limit, minus, well, inverse tangent of 0 is 0, okay, plus, right, the tangent inverse of 0, okay, minus, and then tangent inverse of, as we go to negative infinity, is down here, right? And this is negative pi over 2. So minus a negative pi over 2. All right. So we'll have pi over 2 minus a negative pi over 2. And that is going to be pi. So this interval converges. So that it converges to pi. All right. So that's what we have there. So that's a very popular, very standard improper integral to deal with. Okay. So let's see here. I have a third example. Okay, and I understand that it's tiring. It's difficult to keep writing limits when you have to. I understand that. But this is the class where you get to show me that you can do all of that stuff and you understand what's going on with writing limits. Okay. So here we go. We have integral 0 to 1. You'll stop doing it as soon as you step into another class. You'll never do that again. Okay. But here we have to. Okay. So in this case, right, there's a problem. If there's not an x, right, it's just an x. Okay. There's a little bit of a problem when x, right, is 1. If I plug in 1 here, we have a problem. Okay, 0 is okay, but 1 is not. So we have to write limit. Take your favorite symbol, take your favorite letter. Okay, t goes to 1, and we have 0 to t. Okay, and this is 1 minus x 1/2. All right. Now, at this point, there's a couple of choices we can make. All right. I'd like to just be able to integrate this, but I'm feeling I'm going to lose people if we do that. So we'll say let u is equal to 1 minus x. Du, right, is equal to negative dx. But I also want to do this, right? When x equals 0, right, u is equal to 1 minus 1. So, I'm sorry, 1 minus 0 rather, equals 1. And when x equals 1, then we're going to have u is equal to 1 minus 1, which is 0. Okay, so we're going to replace this integral with u's. Okay. So we're going to say this is the integral, right, of, oh, wait, 1 to 0. Okay. And this is going to be u to the negative 1/2. Okay. Du. We need a negative here, don't we? Which is nice because I'm going to keep my limit. Right? This is still my limit. As in this case, as t goes to 0. Okay, I guess we could pick a different letter, right? Because now we're dealing with U space, but it's not like we need to conserve letters. Okay, but there we go. It's -1 to t, because when u is equal to 0, we have problems. Okay, we have du. We have a negative number out here, so I'm going to go ahead and swap my limits to deal with this. So we're going to have t going up to 1, u to the -1/2. Okay. All right. So let's go ahead. Oh, du. Let's go ahead and integrate now. Okay, we took care of the negative. We have the right limits. We're all set. So we have u to the 1/2, and I think we have a 2 up front, right? Because it's going to be 1/2 over 1/2, and 1 over 1/2 is really 2. And then we have t and 1. We have limit, right? As t goes to 0. Okay, so let's finish this off. We have 2 times 1 to the 1/2 minus the limit as t approaches 0 of 2 t to the 1/2. Oh, this is great. This is square root of 1. No problem. 2. And this is the square root of 0, right? You can just do direct substitution on this. So our answer here is 2. The integral converges. Okay, and converges to 2. And then we're set. So sometimes it's useful to change the limits of integration. Sometimes it isn't. But, you could always go back and check that out and do that. Okay. Right. Let's try this one. Now, the next step, your book doesn't ask a lot of these. My book did. But I like these problems. I think they're kind of cool. Okay. They're a little sneaky. But I promise you that there's not going to be a ton of these because you don't get quizzed on this. You don't have a lot of chances to practice this in your homework. Okay. We're going to go from 0 to 2. And we have a 1 over, and we have x minus 1 squared with the x here. Okay. So there's a problem, right? When x equals 1, right, we have a problem. Okay. By the way, this is what cost me a grade and cost me a whole grade in Calc 3, was integrating over this and not seeing the fact that x was equal to 1, and that was a problem. So from now on, I will know, do not integrate over singularities, because it did. It cost me a whole, from an A to a B in that class because of this stupid mistake. All right, so we're going to go from 0 to 1 of dx, and then we have x minus 1 squared plus, and then we have 1 to 0, or 1 to 2, okay, dx over x minus 1 squared. Okay, if you're sports fans, or if you know people who are sports fans, I blame this mistake on costing me a whole grade in Calc 3, but the problem is I let it get that close that mistake could have cost me an entire grade in Calc 3. So the sports analogy is you can't blame a game on officiating, because if the bad call or two happens to everybody, and that costs you your game, I could have gone either way. It's not that call. Okay, it's you blew it fair and square. All right, what do we want to do with this thing? What I'd like to do off to the side here is I'd like to just evaluate, like, what's the x minus 1 squared integral, like an improper, or just a general integral without limits. Okay, and oops, -2, right? What do we do with this? Right, we'll say let u is equal to x minus 1. Du is equal to x. Okay, So really we have integral of 1 over u squared, or u to the negative 2. Let's write that instead. We're going to look at a calculus problem. du. And if we just integrate this as a, an integral without limits, we're just going to have negative u to the negative 1 plus c. Okay. Or if we had an a and a b in here, right, we'd have a negative u to the negative 1 from a to b, and then we can go put that back in. This is negative x minus 1 to the negative 1 from a to b. Okay, so just putting that off to the side, so maybe I don't have to do quite as much work here. I know what the integral is going to be, and I can keep my limits, and it's not going to be as bad writing all of this stuff out. Okay, so we're going to have limit, and we're going to say, again, pick your favorite letter. Okay, how about we pick A is going from 1, 0 to 1. We'll go from 1 to the left. Okay, and integral from 0 to a, let dx over x minus 1 squared, plus, I'll put this on the next line, we'll say limit as b goes from 1 to the right, and this will be b to 2, and we'll have dx x minus 1 squared. Okay, and then we're set. This is why I went through and did all of this, because I didn't want to have to integrate this thing twice. I mean, you wouldn't do that anyway, but it's one of those things, showing your work and saying, okay, I can't integrate this thing, I just don't want to do it twice. We're just going to see, right, every time we do this, just see this thing over here. Okay. So what are we going to have? We're going to have the limit as a goes to 1 from infinity, okay? And we're going to have negative 1 over x minus 1. That's what this is. This is evaluated at a, and then minus, but minus a negative, right? 1 over x minus 1, or 0 minus 1, 0. Here. Okay. Oh, let's go ahead, not even there. Mess this up. I don't want to do that. I want to say there's a here. So if you can go ahead and substitute it, since we have this, right, we can substitute our a or our b and our this b and a over here. So plus, because we are adding the integrals, okay, and we have negative 1 over 2 minus 1 minus a negative, and we have limit as b approaches 1 from the right, and this is 1 over b minus 1. All right. So when I try, so you remember from Calc 1, right? You can't add infinities. It doesn't work that way. Okay, if you're going to do any of that, you're going to need L'Hopital's. But right here, right, you've got a diverges and a negative 1, and a negative 1, and we have a diverges. There's really not a whole lot I could do with that. This integral diverges, and we're done. So that's what we're doing. Now, if I could evaluate this and this to see what's going on, but I can't really do that. Well, maybe. I mean, we have infinity minus negative infinity. Infinity minus infinity here. But usually don't put a whole lot of thought into that. Okay. So there we go. Okay, I want to compare and contrast 3 different integrals for us here. Okay, so what we're going to do is we're going to take a look at 1 to infinity of 1 over x dx. We're going to look for 1 to infinity of 1 over the square root of x dx. And we're going to look at 1 over infinity, right, of 1 over x squared dx. Now, we've already seen that this one diverges, right? We have limit as t goes to infinity of 1 to t of 1 over x dx. This is equal to the natural log. Since it's positive, I'm not going to go with the absolute values. So this is the natural log of x going from 1 to b, limit as t, limit b. T goes to infinity, and this is equal to natural log of t, limit as t goes to infinity, minus natural log of 1, and this was divergent. Okay. Let's take a look at this one. So we're going to have limit, right, as t goes to infinity of 1 to infinity, and this is x to the negative 1/2 dx, yeah? So let's go ahead and integrate that out. So that's going to give us limit as t goes to infinity of x to the 1/2 divided by half. That's going to give us a 2, right? And we're going from 1 to t. So this is going to be 2 times t to the 1/2 limit as t goes off to infinity minus 2 times 1. Okay, the square root of 1. But we know what the square root function looks like. This goes up, up, and away. So we end up with an infinity here. This thing diverges. All right, so this one diverged. This one diverged. What about this one? Right, what about 1 over x squared? Excuse me. Okay, so we have limit. How about we do s goes to infinity? 1 to s. We have 1 over, we have x to the negative 2, right? Let's go ahead and do that. So that's going to be negative x to the negative 1. Limit s goes to infinity from 1 to s. But since I have a negative sign in here, we're going to go ahead and change that around. So that's going to be 1 over x from s to 1, limit as s goes to infinity. Okay, so that's going to be, if I plug in a 1, 1 minus 1 over s, limit s goes to infinity. Well, I know this one, right? The limit is 1 over s as s goes to infinity. This is goes 0. So that equals 1. This converged to 1. Right? That's a very important product. That's a very important result. Okay, so no, of course I didn't. Really? Nah, I didn't do it. It's summarizing. Okay, so if you have a 1 to infinity of 1 over x to the p, chapter 11, you'll see about why it's p. Maybe chapter 10 in your book. Okay. If p is greater than or equal to 1, then this interval diverges. Otherwise, 0, oops, not equal to, because 1 over x to the 0 would be silly. P less than 1 is converges to some value. I don't know exactly what it's going to be. It's going to depend a lot on other factors and coefficients here. Okay, but yeah, in the next series, in the next chapter, we get the series. This is going to be called the p-test, and you're going to be doing this a lot. Okay, so this is an important result for us to know, right, when it diverges and when it converges. Okay, the 1 over x part is kind of it's a very anti-intuitive sort of a result, you know, when we get to the series part. But there we go with that. Okay. Oh, I have one more for us. One more. This is kind of a cheaty way of doing it. Okay. So. All right. So again, we have a 0 to a 4, and I have e to the negative square root of x, okay, divided by the square root of x dx. All right. So I'm going to go ahead and go off to the side and do some U substitution business here, because that'll take care of this. if I wanted to, I could go through and find the limit, right? Because when x is 0, that's not going to be good. I should probably replace this thing with a limit. We still will, but we're going to go off to the side here and say let u equal, if you want it to be positive or negative, I let it be negative square root of x, which is negative 1, which is negative x to the negative 1/2 power. No, positive. All right. And then my du, right? So we have a negative x to the 1/2 is negative 1/2 x to the negative 1/2 dx. And then following along with how your book does this, we have negative 2 x to the 1/2 du, right? We just multiplied through because we're just going to replace our dx with this business. Okay. And the other thing I'm going to do is say, well, when x equals 0, u is equal to 0. Excuse me. And when x equals 4, u is equal to 2. Right? Because negative 2. Just right here. Okay, it's technically negative 0, 2, but we don't have to worry about negative 2's. All right. Or I'm sorry, we don't have to worry about, yeah, we're okay. All right, so let's go ahead and change our integral. So we have 0. So when x was 0, u was 0. When x was 4, u was negative 2. And then here we have a e to the u. We have a square root of x down here. And what was my dx? We're just going to substitute. It's negative 2 x to the 1/2 du. And there's some stuff that cancels, right? So that cancels. We can move this negative 2 to the outside. So we have negative 2. Now we have 0 to negative 2, e to the u du. Now, technically, because we have our u substitution and we no longer have an improper integral because u is defined at all these points, I think we're okay. I don't think you need to use a limit here. All right. I might be wrong because the original function does that, but I think we're safe to not use a limit in this case. So that's just going to be e to the u, negative 2, from 0 to negative 2, and we're going to go ahead and just change this. All right. And yeah, I think we're set. I think this is just going to be 2u. We're just going to have a 2 e to the 0 minus 2 e to the negative 2. So it's going to be 2 minus 2 over e squared. I don't think we really need to do much more than that. Because like I said, we took care of the improper part of the integral. These limits are fine. So I don't think we have to do that. Okay. So that's our, that's the improper integral for that one. Okay. So just to kind of review a little bit, all right. This result here, okay, of the, the p-test is what they call it later on. But if your powers are 1 or more, I'm sorry, if your power is, did I write that? I did not write that correctly. Oh my goodness. I was thinking of something else. That wasn't good, right? When p was less than or equal to 1, right? Because when p was a half, right? When p was a half, we diverged. I got that backwards. That was terrible. It was greater than 1. Erase. It's greater than 1. then we're converges. Okay, so, and it doesn't have to be much bigger than 1, like 1.001, right? It's going to converge, but slowly. But if it's anything smaller than 1, like x to the 0.999, that's going to, right, that's going to diverge like the other ones did here. Okay, so that's something to remember for that one. All right. So yeah, that's an important result. And then the other thing you have to be careful of is, like I said, be cautious of this. Like your homework doesn't have a whole bunch of these, but these do pop up, and they will bite you when you least expect it. So if you have one of these that are kind of in the middle, you got to be careful. Okay. And then the rest of these are pretty, I won't say they're always straightforward, because they're not. Okay. But, negative infinity to positive infinity, I hated these. These were so tedious, because you have to break them up and then do 2 integrals. Okay. So yeah, I'm glad I caught this piece, because that was terrible. That was wrong. Okay. I don't know. I think that's about it. Let's see. What do we have left? We will cover numerical integration tomorrow. And then after that, I think we're going on to chapter 8. Okay. That'll be next week. All right. So I'm going to go ahead and stop recording here. All right. And we'll be good for that.